All right, good morning, everyone. Hope you had a good spring break. All right, so we're going to talk again about convolution. And we first saw this, the lecture before the break. So the main idea is that we have some sort of template function, which is showing a pattern. And we're looking to see where we might find that pattern or something close to it within a signal. So we essentially slide this pattern around different locations, and when it's at a given location, we take a multiply between all the pixels of the pattern and the corresponding pixels below them of the image, and we sum those multiplications all up. And that operation we can refer to as correlation. At least that's what it's called in the signal processing literature, and it has this equation. And so here we're using K1 and K2 to index the locations within the template, and we're using J1 and J2 to refer to the location within the image. Okay, and so here you can see we're doing, so like the output at J1 and J2 corresponds to the input at J1 and J2, but then it's offset by all the different locations within the template, and we sum across all those different template locations. All right, so that's the main equation. And we said we wanted to link this to some terminology from signal processing. So in signal processing, that exact operation is called two-dimensional correlation. And there's a similar operation that differs only in that you reverse the signs here, and that is referred to as convolution. And so because that's the only difference between these operations, and because you can think about when you change the plus to a minus, it essentially means that you're doing this operation here, except it's like you're flipping that template around. You're reversing the horizontal and vertical of it. So you can think about this as convolution without flipping, reversal, and this is convolution with flipping and reversal. Okay, so that's just kind of the terminology. And when we do machine learning, deep learning, it doesn't really help us to have the minuses here. And so instead, frameworks like PyTorch, TensorFlow, and so on, they really implement this. But they still call it convolution. I don't know why they call it convolution and not correlation, but that's what they call it. So it's just something to be aware of. And one last thing is, often in terms of the notation, we use this asterisk here to denote convolution. So sometimes we'll see that in the notes. Okay, so that's some of the terminology. And then we saw that we also have to be a bit careful about how we handle the boundary conditions. So in these pictures, the kernel is the dark blue. The underlying image is the lighter blue, and then the output image is this one. So in this case, on the left, called valid mode, we don't use any zero padding. And so there's only 4 different shifts that we can use for this kernel. So it could be there, we could move it over here, we could move it over here, or we could move it over here. And with those 4 shifts, there's 4 output pixels, and that's it. So what happened here is that the image size shrunk from the input to the output as a result of convolution. And that's something that maybe we don't want to happen, especially if we have many convolutions in a row, then our image keeps shrinking, shrinking, and shrinking. So a more popular alternative is to use what's called same mode. And here what you do is you pad your input image with zeros around the edge, and you use just enough zeros so that the input and output images are the same size. And the number of zeros you need would be the width of the kernel minus 1, that thing divided by 2. And that would give you just enough zeros so that you could do convolution without changing the image size. Now there's another alternative that you see in the signal processing literature where you use basically as much zero padding, use the maximum amount of zero padding so that the edge pixels in the output image correspond to the kernel touching the input image just along 1 pixel wide. So when you do that, this is the maximum size you can get, and so here the image actually grows from input to output. That also might not be so convenient. Also, when you put a lot of zeros in here, it means that the edge pixels here are mostly the result of zeros, and we'll see an example of that. So I would say that this is the most popular alternative in deep learning, although you have these other options. Okay, so, and then here are some, these are examples just showing explicit numbers in the input image, the kernel, and the output image. All right. So that's sort of just catching up from before spring break. And so now let's take a closer look at what happens when we do this 2D convolution in Python. So we're going to start out by using this SK image library. Another related library is a SciPy signal for signal processing. And we're going to do some experiments with this image on the right called the cameraman image. This is an image that's often one of several images that are often used for image processing experiments. This one has some nice sharp lines, and so it's going to be useful for us to see what happens when we do convolution. And we're going to look at 2 types of convolution. The first is going to be local averaging, which essentially causes a blurring of the input signal. And the second is edge detection. So you might say, well, why would we want to blur the signal? That doesn't sound good. And that's true. Blurring is itself not good, but what this can be used for, although we won't show it, is if there's noise in your signal and you process it with a low-pass filter, you can improve the SNR because the signal, like this image here, has a lot of low-frequency energy. And noise typically has energy, equal energy at all frequencies. And so if I process it with a filter that keeps the low-frequency energy and reduces the high-frequency energy, I'm going to reduce my noise much more than I will reduce my signal. And as a result, the signal will look a lot cleaner, although it will look a bit blurrier. Okay, so that's in practice where you might want to do a local averaging filter, but we're going to do it without the noise just to see how the result looks. So we can input this image directly from SK image, and we can display it like this. Okay, so we're going to first build a kernel. It's a pretty boring kernel. It's just going to be a 9x9 kernel that has all ones. So it's all ones, but then we're going to divide by the number of pixels, 81. And so now if you sum up all the entries in the kernel, they sum up to 1, which means that when I slide it around, I'm doing an average of wherever that kernel is sitting. Okay, so this is the original image. And here we're zooming into the top left corner, just to see what happens. So as you can see here, the top left corner is this sort of uniform gray in the original image. So the first thing we can do is we can do convolution. So here's SciPy signal convolve 2D, and we're going to use the full mode. That means we're going to do a bunch of zero padding around the original before we do our convolution. And this is the result. So one thing you can see is that the image got blurrier, so you don't have all the sharp features there. And then when you zoom into the corner here, you can see this strange effect here. This is due to the zero padding. So this color is the same as this, but there's going to be an 8 pixel wide band on both sides where you're averaging this and then the black 0 pixels that you use for zero padding. So you can see this directly from this picture. This is the effect of the zero padding. So it makes this strange boundary. Now, if instead we would have used same mode, then the behavior in the middle of the image is going to be the same, but the behavior on the edge is not as severe. So in this case, we're going to have 4. And also, of course, the image size is going to be the same. So whatever the original image is, this one will have the same size. And finally, if we do the valid mode convolution, you can see we don't have any of these edge effects, which is great, but the image is going to be smaller by 4 pixels in each direction. Okay, and here you can see the input image is, the output image is smaller by 8 pixels in each direction, not 4. So 512 by 512 is the original image shape, and that's what we have for the same mode, but valid is 4 smaller and full is, 8 smaller and full is 8 bigger. Okay, any questions so far? All right, so now let's do another experiment where we change the kernel size from a 9 by 9 to a 15 by 15. We'll do same mode convolution. And what you see overall is that the blurring is much more pronounced with the 15 by 15 because we're taking a bigger window and averaging bigger kernel. We're averaging that. So that's going to take a larger range of pixels and blend them all together to get this. So you can see that the size of this averaging filter affects how much blurring we get. All right. Any questions so far? Okay. Now let's try a slightly more interesting kernel. So instead of a uniform one that had all the pixels the same, we can make a kernel that weights the center pixel more than the edge pixels. And essentially we're going to do this by putting a Gaussian, like a bell curve shape in both directions. So, so as you know, with a Gaussian, there's 2 things you can control: the mean, which is where the center is, and the standard deviation, which is how wide it is. So that's a parameter we're going to have to adjust. And for a given standard deviation, we want to make sure that we choose the size of the kernel wide enough that we see that roll off. We don't want to choose it, if k is really small, then it looks uniform. And if k is really big, then essentially we'll have almost zeros out here. So we want to choose k, close to 2 sigma plus 1 or so. Anyway, so when we do this, here's the uniform kernel from before, and here's the Gaussian kernel. And if you look at the difference here, the Gaussian kernel is giving us slightly more sharper features. And then let's look at the 15 by 15. Once again, you can see there's a bit more sharp features in the Gaussian kernel. And I think it's kind of intuitive because the Gaussian kernel, you're mostly averaging the features in this region, even though it's a 9 by 9. So it's like effectively behaving closer to a uniform kernel that's smaller. Okay, so in practice, we use kernels, or we learn kernels that have shapes that are closer to this than uniform in most cases. We'll see some of the shapes, some of the kernels we learn in AlexNet in a few slides. Okay, any questions on this? All right. So let's do something more interesting now. Let's try to do edge detection. So we can do edge detection, again, using convolution. We just have to build the kernel the right way. And we're going to use these famous kernels called Sobel filters. And there's two different ones. There's one of them, which we'll call GX. That's useful for when you're looking for changes for edges that are vertical edges. So if I have a vertical edge, that means if I go horizontally, I see a change across that edge. And this filter here will detect the change because we have positives, zeros, and negatives. So imagine that I have a change, horizontal change from dark to light. And we know that dark pixels use small values, light pixels use large values. So if I'm doing convolution, and then this is convolution with flipping and reversal, so I have to kind of juggle a few things. You know, we have to juggle a few things in our minds here. So when I do flipping and reversal, essentially what I'm going to do is I'm going to flip this left to right and up, down. Okay, the up-down direction you can see is symmetric, so flipping it up and down doesn't do anything. Flipping it left to right means I'll have the negatives here and the positives here. Now, if I have a horizontal change from dark to light, I'm going to have negatives multiplying small numbers and positives multiplying large numbers, which means I should see overall a number greater than 0 if I'm going from dark to light. Meanwhile, if I go from light to dark, the sign is reversed. I get something less than 0. Okay, so that's what happens with this filter. And we didn't talk about what happens vertically. So essentially what it's doing is it's putting more weight on the center pixels here than it's, like the changes you see in the center pixels than the weight it's putting on the changes you see in the top and bottom pixels. So it's sort of focused more on what's happening in the middle of the filter. But it does respond a bit to what's happening above and below the middle. Okay, so this is would be for detecting vertical edges. To detect a horizontal edge, we just flip the filter on its side, and if we have a vertical change from dark to light, then we expect the outputs to be positive, and when we have a vertical change from light to dark, we expect the outputs to be negative. Okay, so let's look at the results of this. So, this first one is, okay, I guess we're going to do both GX, which detects the vertical edges, and GY, which detects horizontal. And so here you can see that we have a change from light to dark across that edge. It's not perfectly vertical. Let's see. Okay, here's one that's closer to vertical right here. So if I go from light to dark, we said we expected the filter to put out a negative. And here's that negative. We see there's a dark line. On the other hand, if I look at what happens over here, I'm going from dark to light, then we see white, which is positive. And if I have a horizontal edge, we don't see it at all, because this filter is detecting vertical edges, and it's blind to horizontal edges. On the other hand, this filter here detects horizontal edges, but it's blind to vertical ones. Vertical ones, I don't know if we see, we don't have any great, here's some examples. This building here, you can't see the edges at all. Okay, so this is how we can do edge detection, which is just, another thing you can do with convolution. This is the one with flipping and reversal, convolve. If we do correlate, which removes flipping and reversal, then we expect the dark to turn to light and vice versa, and that's exactly what you see. So this dark line now becomes light, and the light lines become dark. So everything is sort of working as expected. All right, any questions? All right, so this is all just to try to understand what convolution is doing. Okay, we'll return. We have one more interesting convolution experiment on a color image that we'll get to probably towards the end of the lecture. Okay, so coming back to these convolutional deep neural networks, this is AlexNet that we've seen before. And so now we can talk, now that we know about convolution, we can talk in more detail about exactly what's happening as we go from one layer to the next. And again, remember that when we look at these pictures, they're a little different than our typical block diagrams we see in signal processing. So the blue things here are representing the data itself, and they're showing us the dimensions of the data. So we're starting with a color image of 224 by 224 pixels and 3 colors, red, green, blue. So that's what we start with. We go through the first convolutional layer, and we'll talk about this in detail, but we're essentially going to use an 11 by 11 convolutional kernel in that layer. And then we're going to do 2 other things. We're going to do activation, like ReLU, some nonlinear operation. And then we're going to do something that changes the dimensions of the image, or you could say of the feature maps. So we're going to shrink the dimensions by 4, basically, a factor of 4. So we're going to go from 224 by 224 to 55 by 55. And we're going to do that using something called pooling, which we'll talk about. And then we do that a number of times. And then at the end, we're going to switch the operation to these fully connected or dense layers. And they work exactly like the 2-layer network in the last unit, where each layer, where we'll do matrix multiplication first, and then activation. The activation still is typically ReLU. So no convolution in these final layers. Okay. All right, any questions, high-level questions before we dive into the details? Okay, so first let's just briefly talk a little bit more about tensors. So what we said is you can think of each of these blue objects as a tensor. A tensor is really just a multi-dimensional array. You know, a matrix would be a 2-dimensional array, but these things that we're drawing here have 3 dimensions. Right? They have like height, width. We can call these things channels. 3 colors. So, yeah. So a grayscale image, like an MNIST image or that cameraman image, just has height and width, right? You can represent it as a matrix. Color image, you need height, width, but you also need a channel index. It tells you the red, green, and blue pixels. Now, when we push data through this network, even though we're showing these 3D objects here, there's actually a 4th index, which is we're going to work with mini batches. And so, as a result, we're actually going to be using 4-dimensional tensors. The first dimension is going to index across the images in the mini batch. The next one across the channels, and then the last 2 across the pixels, height and width. Okay, and this ordering, mini batch index, channel, height, width, this is the ordering that PyTorch uses. Okay. So it's very important to know that, because if you mix these things up and you put channels, let's say, at the end, it's going to do something very unexpected. Now, it's also important to know that the SK image library uses a different format. They use height, width, channel. So for them, channel comes after height, width, right? So that means whenever you work with both of these libraries, you actually have to do a conversion. If you maybe do some stuff in skimage first, well, then before you go to PyTorch, you have to move this over here, and we'll show you how to do that in some code. Okay, so terminology-wise, the number of dimensions in a tensor, some people call it the degree of the tensor, or the order of the tensor, or the rank of the tensor. Rank is kind of a tricky term because with matrices, if I tell you this matrix has a rank, that's, that has a particular meaning. And the meaning is very different than the meaning here. With tensors, the rank, you're simply counting the number 1, 2, 3 of dimensions. So just be aware of that. Okay, the shape of a tensor tells you exactly how many elements you have in each dimension. So if I have a 10 by 20 by 4 tensor, the shape would just be the triple 10, 20, 4. And we could say that the degree of this is 3. And these tensors are basic data types in Python. So when we've been working with NumPy, we've always been working with ND arrays. These are just n-dimensional arrays, basically tensors. They can have any degree you want. Typically we use 1, 2, maybe 3, but you could have as many as you want. And in PyTorch, the corresponding object is the torch tensor. It can have as many, a degree as large as you want. Okay. All right, so now let's talk about convolutional layers. So this is a little tricky, so let's make sure that you guys ask questions and get to the bottom of this. Okay, so the convolutional layer has a weight tensor. So this is like the kernel. The weight tensor has a degree of 4. It has the first, it's number of output channels by number of input channels by the pixel size K1 by K2, like number of rows, number of columns. Okay. And then there's a bias vector that's just a degree 1, just a vector which has C out elements. And this equation here shows what happens when we do convolution. So the input to our convolution is coming from the previous layer, and we called that A in the last unit, the activations from the previous layer. So just like we discussed, the activations themselves is going to be a 4-degree tensor. So the first indexes across the mini batch. The second indexes across channels. So because this is the input tensor, these are going to be the input channels. And then the last 2 dimensions index across the pixels, the vertical pixels and the horizontal pixels. Okay, so that's what's coming in. We're processing it with W, and then we output a tensor Z that essentially has the same kind of ordering as the input. So I is going to index the mini batch, M is going to index the output channels, and now there's going to be C out of them, and then J1, J2 are going to index the pixels, vertical, horizontal. Okay, so let's break this down into sort of 2 parts. Let's focus on what happens in the last 2 dimensions here and here. So if you focus on the last 2 dimensions, it's exactly convolution as we defined it a couple slides ago. Right? Just ignore the first 2 dimensions. So here you have your output pixel indices, kernel, template pixel indices, and here's our correlations because we're using pluses. Okay, so if I had a single batch element and 1 input channel and 1 output channel, all we're doing is convolution, as we learned it. So the next question is, what happens when you have more than 1 input and output channel? essentially, you're doing a separate convolution from each input to each output channel using a separate kernel. Okay, so this kernel would be the kernel that is taking you from input channel N to output channel M. And here you can see we're using the input channel N, and we're putting things in output channel M. And that kernel has a full set of weights, K1 and K2, right, for that combination of M and N. So in total, when we have this convolutional layer, we're actually doing C out times Cn different convolutions. And then the last thing we're doing is, for a fixed output channel index, we're going to sum over all the input channels. Okay, so if we want to say this in words, for each output channel M, what we do is the following. We correlate each input channel N using the K1 by K2 kernel WMN, and then we sum the results across the input channels N, across all of them. And we do that for every fixed output channel M. Finally, we do this same operation for every batch element I. So across the batch elements, it's very boring. We just do it separately for each I. So what's really more interesting is what happens across the channels. So maybe coming back to this picture here, what we have is we have an 11 by 11 kernel, right? But notice we have 3 input channels, 96 output channels. That means for every combination of input to output channel, I have an 11 by 11 kernel. So the total number of 11 by 11 kernels I will need to use and to learn is 3 times 96. And if I look at what happens at a specific channel and a specific pixel in the output, that's going to be this 11 by 11 kernel located at a particular location that's going to map to that pixel. I'm going to have actually 3 of those, one for each of these channels, and they're all going to be summed together to get that pixel value. Okay, so I know this slide is not easy. Get a lot of questions about this. So, you guys have any questions? Yes.
What's the difference between C out, C in, and P?
Yeah, C out and C in are, so in this case, like if I'm talking about this convolution, C out would be the number of channels here, which is 96. C in is the number of channels here, which is 3. And when I work on a GPU, actually forget about that. We discussed in the last unit, when we do gradient descent, we want to work on many images in a mini batch. We want to do one gradient update for all those images in the mini batch. So I'm gonna have, if I have a mini batch of, let's say, 128, I'm gonna have 128 different images of this size. And they're all gonna go through the same convolution operation. So that's not shown in this picture, but you just kind of keep it in your mind that we're doing this to a batch of 128 or so images. And that's that last dimension. All right, some more questions? Yes?
Can you explain again how you got from the 3 channels to 96 channels?
Yeah, so like in this equation, I'm going to have 3 channels. So I'm going to do a sum over 3 different channels. So this will be my original image. Actually, this is going to be the ith of my original images in the mini batch. But that image has red, green, and blue channels, right? So this n is going to index over like red, green, blue. And then it has a bunch of pixels for the red, for the green, and for the blue. And so I'm going to have and then over here, I'm actually growing that to 96 different channels from 3. So like from the red, I'm going to have 96 different kernels that take me from red to a single, from red to all these guys, I'm going to have 96 different kernels. From green to all these guys, I'm going to have another 96. And from blue, another 96. So those are all the different kernels. The way this equation is written is fixing the output channel index. So maybe this is the first out of 96. And I'm going to sum across the red, green, and blue convolved outputs. Does that answer questions, or kind of?
So the 96 you just kind of chose, like it doesn't need to be 96 for any reason?
Exactly. 96 was something that they chose. They chose all these numbers, 96, 256, 384, and so on. These are the hyperparameters of the neural network that are not easy to choose because there's a lot of them, and it's a lot of work to evaluate different pairs. But yeah, there's certain trends that you can see. You can see that essentially one trend is growing the channels from 3 to 96, and then you can see another trend is shrinking the size of the pixels. And some intuition is that we're going to start out with lots of pixels, 224 squared, and we're going to end up with classes, no pixels at all. So somehow we have to transition from many pixels to no pixels at all. But we don't want to just, if I didn't add channels, I would just be losing information because I would just be shrinking the feature representation as I go through. So what they choose to do is by using more channels, you can afford to shrink the pixels and grow the channels in a way that preserves information. And eventually you're going to come down to a list of 1,000 numbers, but as we saw in the last unit, you typically want to have a larger representation in the middle, and then you can shrink back down towards the end. So we start out with whatever image we're given, we finish with however many classes, but in the middle we want to have a large number of numbers here. So 13 times 13 times 384 has to be big enough. If that is too small, we'll have a weak network and it won't really be able to learn what we need. All right.
Why are we, so I see your summation over Cn
Uh-huh.
on the slide. Why are we not summing over C out and B?
So this equation is just written for a specific output index, M. So we're just saying what happens at a particular, this is one particular channel in the output, and this is, one particular pixel location. So we're saying, how did we compute that single number? That single number is going to involve a separate kernel for each one of these input channels. So we're summing across the input channels, but we're fixing the output channel. Okay. Any other questions? Yes.
So why do we separately have a bias vector?
Oh yeah, that's right. We haven't talked about them. So we do have these bias vectors. So what's interesting about the bias is that the bias or the intercept is actually common for all the pixels, right? We use exactly the same value. This guy does not depend on J1 and J2. And that's just what's done typically. Like one could imagine having a separate bias for every pixel location, but that's not what's done. So I think they found that it's enough to have one scalar bias per output channel, and that's all you need. And this cuts down on the number of parameters you have to learn, and I guess it's enough. It doesn't benefit you to have one per output in most cases, one per pixel. But yeah, the role of this is just to I don't know. I guess all along we like with way back in linear regression, logistic regression, we always had that bias term, that shift, that we want to be able to learn a shift to put us, this is all going to go into some activation. If it's shifted weirdly, like if it's shifted to negative and we go through ReLU, then everything just gets turned off. It just gets mapped to 0, which is kind of useless. So we want to be able to make this shift put us in the right spot. And these are all learnable parameters, right? We'll hopefully learn the right things to do at every layer. Okay, making sense? Convolution, all right. Okay, so that's the hardest part. So what we said is, okay, convolution explains how we go from, it's just the first stage in typically 3 different stages. So we do 2D convolution, or actually correlation. Then we do activation, which we know about, putting it through ReLU or something like that. And then we do this last one we'll need to talk about. So this is used to shrink the number of pixels at every layer because, as I said before, we're doing a gradual transformation from the pixel domain to the class domain. And so we just want to kind of reduce the notion of pixels and having many pixels gradually as we go through. So we're going to shrink, usually factors of 2, factor of 4 in this case, then 2, then 2. Okay, so how do we do that shrinking? So there's a few options to do this. And so these are the most popular ones. So there's something we could do called subsampling. And subsampling is pretty easy to describe. Imagine that you break up your image into S by S regions. And what you do is you simply take the top left pixel in each region. Okay. So if you've taken signal processing course like 5200, this is what we call downsampling in that literature. And if I'm taking just one pixel out of an S by S region, then I'm going to shrink by a factor of S horizontally and vertically. And as you can see, there's some disadvantages to this because I'm just literally throwing away all those other pixel values. And I'm not using them at all. Okay, so that's sort of the disadvantage of this. One possible advantage of this is if I know I'm not going to use those values, then I don't ever need to compute them. So that means I can be smart in the way that I do my convolution, and I can make sure that when doing my convolution, I only compute that pixel. Okay. And in signal processing, we call that polyphase. We do that kind of stuff when we do polyphase decimation. Okay. So that's what I mean by here. You can implement this as part of convolution. There's no wasted computations. So in fact, in PyTorch, if you want to do this, you specify this in the convolution layer. You don't specify it as a separate thing. It's actually part of convolution. Okay. But subsampling, because as you can see, we're choosing to keep one top left pixel. That's maybe not the best thing to do. Maybe we want to somehow use all those values and do something more holistic. So a more popular alternative is max pooling. So here we're going to keep one of those elements in each S by S region. We're going to keep the largest one. So we're going to do a search over this region, find the largest one, and keep that. Then we'll do a search over this region, find the largest one, and keep that, and so on. Also, we can decouple the size of the region from the amount of shift across regions. So we can use K by K regions and shift them by S horizontally and vertically. So let me show you an illustration of that. So imagine that this is our image or a part of a larger image, and these are the pixel values. And we're going to do max pooling. Let's say we're going to use K by K. We're going to use a 2 by 2. So that would be, meaning in this little window, we're going to look for the largest value, which is 5. We'll keep 5. Then we're going to slide over by the stride, which could be 2 again. Now I look at the largest one in this region, which is 4, and I keep that, and so on. I shift down by 2, look for the largest one here, 4, keep that, and so on. But as I said, we can decouple the size of the search from the shift. So down here, I have a, I have a 3 by 3 image over which I'm doing my search. And in this case, it's 5 again. And then I'm going to slide it over by 2. So now I have this 3 by 3. And so here we don't exactly know the values of these pixels. At least they weren't specified in this example, so it's hard to know what the max is going to be, but it's going to be something in this 3 by 3. And then our stride is still 2, so we move down by 2, and then we again move over by 2. Okay, so this is basically just saying you can use, for example, a 3 by 3 region, but you can shift it by 2 horizontally and vertically. And this is what they used in AlexNet. They use max pooling. Now there's, yeah.
So in that case, our region has to be at least as big as the stride?
The region, I don't know if it needs to, but it would probably be a good idea for the region. Like implementation-wise, PyTorch may allow you to have a 2 by 2 region and then move it, In fact, you could argue that what this is doing is it has a 1 by 1 region, and you're shifting it by S. So, but yeah, probably when people use max pooling, K is going to be equal or greater than S in practice. Okay, so another option would be average pooling. Average pooling, instead of keeping the largest value in each K by K region, you just keep the average value of that region. And in signal processing, we would call this decimation. Okay, and then finally, this operation, you're going to do this independently on every channel and in every batch item. Okay, so again, this is just to, basically you're saying like there's redundancy in the pixel domain because I've grown these extra channels. I'm just going to remove some of that redundancy in the pixel domain, which gives me a smaller image at every layer. Okay, any questions on subsampling? Yes.
Are these SDKs something learned from gradient descent, or are they just like chosen trial and error?
So there's nothing learned here. You can see that, I mean, this is completely deterministic. This is completely deterministic. This is something that does depend on, you know, the exact data you get in that channel and in that batch item. Because you're going to have a different feature map coming at you, and you're going to compute the max in each region, pull out the max. So there's nothing learned, really, but does that answer your question?
So how is S and K selected?
Oh, yeah, this is just the designer. It's one of these hyperparameters. The designer has to choose them. So like they chose to do a pretty big reduction by 4 in each dimension in that first stage. And then they chose to reduce by 2 in every stage after that. So I think we can look at the details, but I believe that I guess 224 to 55 is not exactly like, okay, 55 times 4 would be 220. So there's somehow 4 pixels are getting lost. Maybe they used less padding so that maybe convolution shrunk their image from 224 to 220, and then they downsampled by 4 to get 55, maybe. But you know, this is pretty close to a factor of 4 reduction. And then from here to here, very close to a factor of 2, right? 54 to 27 would be exactly 2. And then another factor of 2 here. So yeah, these values are going to be integers, but there's something you need to choose. And probably the AlexNet people, they just tried various things, and then eventually they settled on those, found those worked the best. All right, any other questions? These, all right. And finally, let's talk about the dense layers. So let's say that the very last convolutional layer produced, after pooling, a tensor of this shape. So we have batch size of B, C output channels, and we have a feature map of N1 by N2 pixels. So what we'll need to do is, as we transition from this half of the network to this one, we need to do what's called a flattening, where you take this 3D tensor and you just unravel it into a 1D tensor. And so, or sometimes it's called flattening. So you just do a simple reshaping of this. Actually, it's from a 4D to a 2D, because we're going to do this separately for every batch item. So basically, this 3D tensor we flatten into a 1D tensor of size C out times N1 times N2. Basically, for every batch item, we just have a vector. And then this guy, N in, is going to be processed just by a matrix multiply. And this is exactly like we saw in the 2-layer neural network from last unit. So here's our learned weight matrix. And this is, again, separate for every batch element I. We just do a matrix multiply between W and this vector. And as before, we add one bias for each output channel. So if you ask, like, what's the connection between dense layers and convolutional layers? Like, is a dense layer a special case of a convolutional layer? Yes. You could say if you have a convolutional layer with a 1x1 kernel and your feature map has 1 pixel vertically and horizontally, then that convolutional layer would reduce to this dense layer. So there is kind of a connection this is a very special case of a convolutional layer. And one of the reasons I'm pointing that out is that we can, if we wanted to treat this as a convolutional layer, just to have kind of a uniform notation, we can do so. We can just think of this as a very special convolutional layer. And so, for example, when we do our back propagation derivation, we can derive everything assuming convolutional layers, even though some of them are dense, and we can just say, well, the dense ones are a special case convolutional. Okay, so that's. Basically, you learned all of this. The only thing new here is this flattening operation. Okay. Any questions? Okay, great. So let's talk about our motivation for using convolution. So one huge motivation is they have many, many fewer parameters than dense layers. So let's just look at a particular example. Let's look at the second layer in AlexNet. So this is a layer where we are going from 96 channels to 256 channels. Our feature maps are 55 by 55 pixels. And what AlexNet uses is they use a 5 by 5 kernel in doing that convolution. So let's count how many weights we have to learn for that layer. So we have, for every kernel, we're going to have 5 by 5 or 25, right? But how many kernels are we going to have? C out times C in, different kernels. And C out is 256 and C in is 96. So you multiply all those numbers together, you get 6.1 times 10 to the fifth. So basically like 610,000 numbers to learn. Plus, weights, plus the number of biases is just the number of output channels, which is 256. So pretty small relative to this. Okay, now, even though that might sound like a lot, let's think about how many weights we would have if we replace this convolutional layer with a dense layer, a fully connected layer. So when we talk about a dense layer, we just have to say, okay, how many input pixels would I have? Well, that would be 55 squared. How many output pixels would I have? That's 55 squared again. And so the number of weights in that matrix connecting input to output would be the square of those things. So in other words, n1 squared times n2 squared. And when you multiply, and this is going to be a separate one for every input and output channel. When you multiply that together, you get 2.2 times 10 to the 11th. So this is almost 1,000,000 times more weights than the convolutional case. So this is just for one layer in the network, right? This would be super impractical if you had to do this for all the layers, even just for the one layer. So that's one of the huge motivations for doing convolutional layers is you're doing a linear operation. The linear operation is much more restricted, but as a result, it's much more structured, but it's much simpler. Now, of course, we could worry about the restriction. We might say, well, we're going to lose a lot of, we could learn a lot of dense matrices that are impossible to learn in the convolutional case, and that's true. So the main thing we would like out of our convolutional layers is that whole idea of the pattern matching, the template. That's what's going to give us what we call translational invariance, which means we're looking for these local patterns that are relatively small, and they could be located anywhere. That's the main idea behind the pattern matching concept. That is preserved by convolution. When you do this full dense matrix multiply, you can do way more than that. But maybe all we need to do is translation invariance. All we need to do is convolution. And again, when we look at things like the human brain and we look at what it's doing, it's essentially doing convolution. It's not doing like dense matrix multiplications at every layer. So maybe with that inspiration, It's a really good trade-off. It's a very small fraction of what you have to learn, but it does a really good job of learning what needs to be learned. But then there's the question, why can't we use convolution all the way throughout? And actually, it turns out that you can. They didn't do this in the early networks like AlexNet, but if you look at the evolution of neural networks after that, the dense layers often were like disappearing. Fewer and fewer dense layers. But at least in the beginning, when people were first creating these, they thought, well, the features that I'm learning towards the end are not really local features, they're these global features, and maybe I don't want to impose some local structure on them. So maybe instead I want to just look at them globally. So I don't want to do convolution. That was their thinking. So that's why they have those dense layers at the end. But like I said, there's now fully convolutional networks that work, even better than these early ones. So that's something that over time people change their mind about. Okay, but that's again the main idea. Many fewer parameters to learn, but we can still exploit translational variance. Okay, so I'm sorry I went a little bit too late today. So I think that's a good place to stop. So we'll get into some PyTorch details next time, and then we'll see a nice example of what happens with color image convolution, which will give you, again, more experience and intuition behind having multiple input channels and multiple output channels and what that means. All right, so enough for today. We'll see you guys on Wednesday.